Hello, this is Graham Neubig and welcome back to CS 11747, Neural Networks for NLP. This time we'll be talking about structured prediction with local dependencies. And in particular, I'm going to be talking about a very widely used model called Conditional Random Fields, or CRFs. So previously we've talked about a prediction problem where we take in a text and want to predict labels, or in other words, text classification. So this is a simple problem, and the particular type of prediction it belongs to is going to be either something we call binary classification, where we take in an input and try to predict one of two labels, or multi-class classification, where we take in a prediction and try to predict one of many labels. However, there's a other very important variety of prediction called structured prediction, where we have an exponential or infinite number of labels in a prediction task. So this could include things like part-of-speech tagging, where we take in words of an input and try to predict part-of-speech tags for each of the words. And it could also consist of things like machine translation, where we take in an input and try to output a sentence in a different language. And the first of these two problems, it has essentially an exponential label space because we have each word has a fixed number of potential part-of-speech tags, and then we have a combination of all of the part-of-speech tags for all of the words in the input. The second one has a potentially infinite space just because we have no explicit limit on the length of our output. So now our output could be, any size, including infinitely long. So why do we call these structured prediction problems? We might not normally think of a flat token sequence from text as a structure, but basically the reason why is because classes are too numerous to enumerate all of them. And so we need some sort of method to exploit the problem structure to learn efficiently. So we might exploit the fact that each of the tokens in the output space, it essentially has its own meaning, and try to predict the tokens one by one. And so, one example of this would be parts of speech, where we look at the parts of speech and say, these two sequences are very similar because all of them have a preposition and a verb in the first two words and a noun in the last word. So there are many varieties of structured prediction. We can use different models. So in fact, the translation models that we've already talked about, RNN-based decoders or transformer-based decoders, are one variety of a structured prediction model. We can also have conditional random fields, which we'll be talking about today. We can have training algorithms, so we can have maximum likelihood with teacher forcing, which we've used a lot before, sequence level likelihood with dynamic programs, which we're going to talk about today, and also reinforcement learning, minimum risk training, and other methods like this. So as I said, some of these we've covered already, and these two are going to be things that we cover today. So as an example structured prediction problem, I'm going to be using sequence labeling, which is a very important problem in kind of NLP in general. And the way it works is we have one tag for each word, such as part-of-speech tagging. And so we take in an input sentence and we try to predict one tag for each word. It could also be something like named entity recognition. And named entity recognition is basically the task of trying to predict people, places, organizations, or other varieties of entities that are kind of proper nouns. And they can be multi-word expressions as well. So we have Keanu Reeves here, which is a single entity. And the way we usually handle these in NLP models, it doesn't have to be the only way, but the way we usually handle them is by converting this into something called a BIO tagging scheme, where we tag either O, which means that this is not an entity, or B, which means the beginning of a particular type of entity, together with the label, or I, which means we're inside an entity with a particular label. And we can then convert these back into the spans that we're trying to model. So one thing about structured prediction models, essentially, is they're models that model interactions in the outputs. So one way to handle sequence labeling tasks would be to use a RNN-based like encoder and then independently predict the tags. But this would not be able to model the fact that particular interactions exist in the output. And the reason why this is important is because consistency within the outputs is important. So for example, here we have time flies like an arrow. This is a famous kind of syntactically ambiguous phrase where if we take the standard metaphorical sense of this, we would get this part of speech sequence, but we could also get a number of different part of speech sequences. So the first one, it means time moves similarly to an arrow. The second one, it means that we have time flies, some strange variety of flies that are fond of arrows. And the final one is a command form, which is basically saying, please measure the time of flies similarly to how an arrow would. So if we consider the interactions between the outputs, some of these are all natural outputs, but like let's say we had a model that was somewhat confused about which output this should be. So it essentially assigns a probability to the highest probability part of speech tag independent of all of the others. And if it did this, we would actually get something that looks a little bit like this, which is different than any of the other possibilities that we thought were reasonable. In other words, time flies that are similar to an arrow, and there's no verb in this entire sentence, so maybe this would not be the best analysis. And this is a rather contrived example, but there are plenty of much more natural examples. So for example, it's rather difficult, for example, to do translation without considering the interaction between the multiple words in the output. So that's one example where these structured prediction models are very important. So sequence labeling is independent classification, as I slightly mentioned before, could take in all of the inputs, run them through classifiers that take a surrounding context window and predict the output. And this does actually work to some extent, but it has the problem of essentially not being able to handle the interactions between the outputs. So it's a structured prediction task, but the model itself is just a simple multi-class classifier over the space of part of speech tags. Even if we add a BILSTM on top, this is still not necessarily a structured prediction model, because each of the outputs are predicted independently, and we're not considering the interaction between each of the outputs. So this is a little bit hard conceptually at first, perhaps, but what you should remember is an LSTM is just a feature extractor. It doesn't have it's not making any predictions yet. So it's just extracting features from the input, and then all of these predictions are being made independently, and there's no dependence between, for example, that preposition was predicted first and verb was predicted next. So one way we could solve this problem and turn it into an actual structured prediction model is by adding a recurrent neural network-based decoder. And the way this works is, or the way this would work if you chose to use this way, would be like an encoder-decoder model. You would essentially take the previous part of speech and feed it into a forward recurrent neural network or some other variety of model to predict the next tag, and then you just, every time you predict a tag, you would feed it back into the model so that the model could use this information when it makes its next prediction. And this is a very reasonable proposition. This is what we actually use in translation largely. However, it does have a few issues. So independent classification models make strong independence assumptions, no guarantee of valid or consistent structures, as I said before. History-based or sequence models make no independence assumptions, and because of this, you cannot exactly calculate them. They require approximate search, such as beam search, and they're also prone to an issue called exposure bias. And what do we mean by exposure bias? Exposure bias, or let me first explain teacher forcing. So teacher forcing basically is the standard way of training our kind of sequence models, or any model that feeds in the output back into the neural network. And the standard way of doing this is that the system is trained receiving only the correct inputs during training time. And this has some advantages. It's very fast because we can kind of already know what our input is going to be before we train the models, so we could do things like efficient training of models using accelerated RNN implementations or transformers or something like this that just read in the whole sequence all at once on the GPU and process the whole thing at a time. However, the issue with this method is that at inference time, it receives the previous predictions, and these previous predictions could be wrong. So despite the fact that it's only taught or only trained on correct inputs, when we're using predictions in the pipeline, these might be wrong. And because the model has never been exposed to these errors, it can fail. So to give an example, let's say we have our previous model, and instead of this being predicted as a just regular present tense verb, it's predicted as a present progressive verb. That might make a mistake. It might cause a mistake over the rest of the sentence, for example. Okay, so I've talked about this, and there's actually a number of different ways to solve this problem, but one popular way to solve this problem is to use something called models, conditional random fields, or more generally, models with local dependencies. And so the way this works is, in contrast to completely independent models, which assume that each output is independent, we make some independence assumptions about the output space, but not entirely, assuming that they're independent. So we only have local dependencies. And the reason why this is good is this can then allow us to do exact and optimal decoding and training via dynamic programs. And conditional random fields are a good example of this. So before I get into conditional random fields, kind of the details of them, I'd like to talk on a higher level about the difference between something called locally normalized models and globally normalized models. So locally normalized models are models where each decision made by the model has, each individual decision by the model has a probability that adds up to 1. And most of the models that we've talked about so far fall in this category. For example, the language models that we've talked about so far, we've calculated the probability of the next word, and we've normalized this probability using a softmax. And the softmax essentially calculates over the vocabulary, so the normalizer down here is all of the words in the vocabulary. And then we multiply all of these probabilities together and to get our final probability of the output. A globally normalized model, which are also known as energy-based models, have each sequence have a score, and this score is not normalized over a particular decision, but rather we normalize the model at the end of generating the sequence or using the entire score. So this is an example here. So basically we sum all of the scores from all of the decisions and then normalize over all of the sequences in the vocabulary, allowed by the vocabulary. So one issue with these models, however, is while calculating the normalized probability here is slow but still possible, is because we are only summing over all of the words in the vocabulary. However, down here, we're not summing over all of the words in the vocabulary, but rather summing over all of the sentences in the vocabulary, or all of the sequences in the vocabulary. And because of this, this results in exponential time, essentially, and calculating this just completely naively is not feasible. So conditional random fields are a general form of a globally normalized model where basically we have a score for each input-output pair, and we normalize the score of the input-output pair by all of the scores over all of the possible input-output pairs. So this is kind of a general form that we cannot easily optimize without some additional assumptions. But a common variety of conditional random fields that we use in natural language processing is called a first-order linear conditional random field. And the way this works is we assume some degree of independence between the scores. So in other words, we have scores that are conditioned on the input and consecutive pairs of output tokens or output parts of speech or something like this. And because we do this, we can then sum more effectively and efficiently, essentially. And I'll show how to do this in a second. So this psi here is something we call a potential function. And what the potential function is basically a function that gives us a score for each pair of consecutive outputs. And a way we can calculate it is by taking a score where we have one score that is calculated over the two output values, the pair of output values, the input x and the position, and we multiply this by some sort of weight matrix. And then we additionally have, weight vector, because this ends up giving us a scalar score. And then we have another kind of feature vector that we calculate with only the output at position I itself, the input, and the index. And then we also have a bias for each of the pairs here. And so these features can tell us different things. These transition features can tell us, for example, how natural is a transition between outputs. And to give an example from part of speech tagging, for example, a determiner is very often followed by a noun. So that would be like the dog or something like this. So that would be a very natural transition. So that should probably be given a higher score. And the transition between a determiner and a determiner, like the or the is less likely to happen. And because of this, that would be given a lower score. We also have these emission probabilities, and these emission probabilities are over a single tag, and they're often used to represent things like essentially the tends to be a determiner, or dog tends to be a noun. So if we get dog at position xi, and noun, then that would be given a high score. But if we are given dog at position I and determiner is a tag, that would be given a low score. So we can use neural features in calculating these potential functions. And like if we have yi minus 1 and yi, one way we could express this is by essentially calculating features from a neural network given the input using like a BILSTM or something like this, and then multiply these by features corresponding to each tag transition or each tag. However, this can require a very large number of parameters, so this would require quadratic parameters in the size of the tag set multiplied further by the size of the hidden vector extracted by a neural network, and this could end up being very large. So the more common practice here is to only associate the neural parameters with the emission probabilities and have the transition probabilities basically be conditioned only on the tag pairs. So this gives us quadratic parameters in the size of the tag set and linear in the size of the tag set times the neural network parameters, which is more manageable basically. So for sequence labeling, what this amounts to essentially is now we have a neural feature extractor like a BILSTM, and then we have a graphical model type locally normalized model on top here. So then the question becomes, how can we actually train and generate outputs with this model? And the way we do so is using something called the forward-backward algorithm for training and the Viterbi algorithm for generating outputs. And I'm just going to give a brief sketch here, and if you're interested in learning more about how exactly this works, I'd highly recommend you look at the recommended reading for this class. So the way CRF training and decoding works essentially is we calculate the partition function, we calculate the potential functions for the correct output that we'd like to generate, and then we calculate this partition function down here, where the partition function is basically the thing that we use to normalize our probability over the output. So by doing so, we can calculate this likelihood here and maximize the log likelihood or minimize the negative log likelihood. So the thing on top is actually relatively easy to compute because we already know the correct output sequence. So we can just step through the output sequence, calculate all of the features of the correct sequence, and multiply by the appropriate parts of the feature vector, for example. But the hard thing is to calculate this partition function. So in training, we calculate the partition function, and in decoding, we would like to find the maximum output out of all of the exponential outputs. So both of these are kind of hard problems to do. So the way we do this is we want to go through an output space of y, which grows exponentially with the length of the input sequence. But we can do this in a clever manner by kind of considering the interactions that go on here. So each label depends on the input and the nearby labels, but given the adjacent labels, the others do not matter. So basically, if we know the score of every sequence from y1 to yn minus 1, we can easily compute the score of the sequence y1 to yn. So what we really only need to know is the score of all sequences ending in each possible candidate for yn minus 1. And we can think of this as some sort of pre-calculation that happens before we think about yn, which gives us a nice dynamic program that makes it possible for us to solve this problem. So in the forward calculation of these values, the way this works is basically we have a score at each time step of the score of all of the sequences up to this point. So I'll call this here just as a reference, the score of 1 and n, which is the score of all the sequences ending with nn at time step 1. And the way we calculate this is with the transition potential from S to NN, and then the emission potential of NN given X here. NN at position 1 given X. So we just add these two together, we add these two together, et cetera, until we get to the end of the possible parts of speech. So in the middle parts, it gets a little bit more complicated. And the way it works is basically we add the score of all of the previous time steps possible inputs. So like NN, JJ, VB, LRB, RRB. We assume that this has been pre-calculated before we calculate time step 2. And then we calculate the transition between NN and NN, JJ and NN, VB and NN. And then we also have the emission of emitting NN. And I realize actually this is a typo. This should be Y2 NN. And here we are doing log sum x, which basically is doing the thing at the bottom here. It's taking two log probabilities, exponentiating them, summing them together, and taking the log again. So this is kind of a numerically stable way to combine together log probabilities, but it's essentially equivalent to summing together probabilities. So basically the thing that you need to know is that this can be applied in essentially quadratic time in the number of output labels at each time step. And then in the final part, we do a transition to kind of an end of sentence state. And we calculate the probability of this transition, and this is the final score. So now this final score can be used essentially as the partition function at the end of the sequence. So this cumulative score that we got from the dynamic program that I just described can now be used directly in training the model. So that's great. We subtract this from the log score of the true path to calculate the global log likelihood to use this loss function. So I described the forward steps to calculate this. So we do an initial step to get all of the score for all of the labels at time step 1. We do a bunch of incremental steps halfway through, and then when we get to the end, we combine together all of these probabilities. This was called the forward-backward algorithm because in traditional CRFs, if you wanted to implement them yourself, essentially you would have to implement a backward pass to calculate the gradients of all of the parameters and update them. But fortunately now with neural network toolkits, the neural network toolkit already has handled the bookkeeping and the backward pass in things like this functionality for us. So we only need to implement the forward calculation of the top part in the partition function, and we're all set. If we want to do argmax search, in other words, we want to find the highest scoring output sequence, we can do this in a very similar fashion. But instead of using the log sum x to calculate the value, we use a max to calculate the score, and we use an argmax to keep something that we call back pointers, which allow us to retrace our steps backward through the input. So this is essentially our search algorithm. And unlike beam search or something like this is an exact search algorithm that allows us to exactly find the best scoring path according to the CRF. So to give a case study, there's something called BILSTM-CRFs for sequence labeling, where they build an end-to-end neural model for sequence labeling that requires no feature engineering or data pre-processing. And basically, they have two levels of representations. They have a character level representation, CNN, and a word level representation using a bidirectional LSTM. And so they extract characters, character level information using the CNN, and then do max pooling, and that gives a character representation here. And then they add an LSTM layer forward and backward, and then a CRF layer, like I talked about before. There's a bunch of training details. Maybe I'll skip these in the interest of time. But basically what they show is that for part-of-speech tagging and named entity recognition, this can be pretty effective. So I talked a little bit about essentially linear chain CRFs, one example of conditional random fields. But there could be other data structures that we would like to calculate the probabilities with respect to other than linear chains. So we could have a fully connected lattice or trellis, which is basically what a linear chain CRF looks like. And what we're doing here is we're essentially expanding all of the part-of-speech tags. We have the possibility of transitioning among all of the part-of-speech tags from beginning to end, and all of the paths through this graph essentially are paths that we're considering as candidates. So this is one example of something that we could calculate probabilities with respect to. On the other hand, we could also have something like a sparsely connected lattice or graph. So some examples of this include speech recognition lattices, where we have a speech recognizer that, outputs several candidates that are all connected together in a lattice. And this is very useful for downstream applications for speech that might be doing translation or some other thing like this. And so we could also come up with methods that marginalize over these types of data structures. There are also hypergraphs. So hypergraphs could be something where essentially instead of having single inputs, we could have multiple inputs. And these are used in algorithms like the CKY algorithm for parsing sentences into trees, basically. And we could also have a fully connected graph, like full sequence models. And in these cases, usually dynamic programming is not possible in polynomial time. So anyway, these are interesting structures, and we could become more creative than just creating CRFs over sequences. And because of this, there are also ways to kind of generalize dynamic programming models. So the question becomes what structure to use, and thus also what dynamic programming to perform. So do we want to use this structure, this structure, this structure? And based on this, how do we calculate features that only rely on local context and can be calculated directly based on just the edges we have in the structure? And how do we combine together scores? Do we combine them together with log sum x or max? And there's a concept, mathematical concept called a semi-ring, which essentially is a generalization of this idea. And you could use the log semi-ring to combine together things with log sum x, or something called the tropical semi-ring to combine things together with max. And then there's other ones like the probability semi-ring, the string semi-ring, and things like this. And there's a very nice toolkit that kind of generalizes all of these ideas called PyTorch struct, which allows you to use neural models, but also calculate values in a way that allows you to more generally kind of implement these types of methods. So if this sounded interesting to you, I'd highly encourage you to take a look at this. And based on this, that is all we have for today. For the discussion question, I would like you to think a little bit more about other types of local dependencies that you think would be interesting to model using structured algorithms. So it might be something in the shape of a tree, it might be something in the shape of a graph, or something like this. And based on this, we could decide, like what would the structure look like, what would the features that you would want to calculate look like, and other things like this. So that will be our discussion question for today. And if you want, you could even take a look at PyTorch struct and see what it does before jumping into the question discussion. So thank you very much. That's all I have for today.